Good morning once again. My name is Mr. Chilola. We meet again for our last lesson in the topic of work and energy. This is the lesson number 4 of the topic work and energy. So in this lesson, we are going to look at a very important subtopic of this topic of work and energy. We are going to be discussing the conservation of mechanical energy. Remember that mechanical energy is of two types. So two types. Namely, we have what is called potential energy and kinetic energy, as we discussed in our previous lesson. And the potential energy is further subdivided into gravitational potential energy, which is the energy of a body due to its height, and the strain energy, which occurs in stretchable objects such as springs. The other form of mechanical energy is what we call kinetic energy, which is the energy of a body due to its state of motion. So bodies that are in motion possess a form of mechanical energy called kinetic energy. So in this lesson, we are going to state the law of conservation of mechanical energy. The law, right? A statement which is based on previously done experiments relating to conservation of mechanical energy. Alright? So please be on the lookout for the law of conservation of mechanical energy, because you'll be required to state it. Alright? In an exam, they may ask you state the law of conservation of energy. Alright, so we'll discuss this one in this lesson. Okay? Should be able to state the law of conservation of mechanical energy. Alright? We'll also look at an example of a case. The case in which energy is conserved. Alright? In which energy is conserved. So we'll look at the conservation of energy with an example of an oscillating pendulum as an example in which energy is conserved. Alright? Okay? So we'll look at an example of an oscillating pendulum. But also, at the very end of the lesson, and indeed the topic of work and energy, we are going to look at a theory, a statement of theory, alright, which is called energy or work energy theory, or sometimes is called energy work theory with related examples. Alright, so we are saying in this topic, we are going to look at, in this lesson rather, we are going to look at a statement of conservation of mechanical energy. Alright, so we'll state a law, alright, a law. We'll state a law of conservation of mechanical energy, okay, with an example of an oscillating pendulum, okay, as an example in which energy is conserved. And towards the end of the lesson, we'll look at a theory which is called work energy theory. Sometimes they may ask you in an exam, state the work energy theory or the energy work theory. Whichever comes first is applicable. All right, the work energy theory or sometimes energy work theory. So we're going to explain that with examples. So let me urge you to follow on the lesson up to the end so that you don't miss anything. So what does the law of energy conservation state? You are not meeting this for the first time. You have had this in Form 1 when you were looking at the aspects of energy or different forms of energy. You learned that energy of a body can be changed from one form to another, right, by making use of what are called devices which are called transducers. All right, so you learned this in Form 1 that energy can change from one form to another. For example, energy of movement can result into a different form of energy such as electricity. Energy of chemicals, which you call chemical energy, can be changed into a different form of energy such as kinetic. All right, so energy can be transformed or can be changed from one form to another. All right, so the law of conservation of energy is a statement which you have to commit to your heart because it's very, very examinable. It's highly examinable. They'll ask you a question. You can simply say state. All right, state the law of conservation of energy. So you have to be able to state it, to frame it properly so that the meaning is not lost. So such a statement is, as shown here, the law of conservation of energy. So it states that, please pay attention, look at the words used in the statement. It says the law of energy conservation states energy can neither be created nor destroyed, but can change from one form to another. All right, so you have to be careful with these words, neither nor, because some people miss that. If you replace the word neither with the word either, for example, all right, you replace neither with either, you have missed a point there. All right, I've seen some students saying energy can either be created or destroyed. The moment you do that, you have changed the meaning. All right, so it should read, energy can neither be created nor destroyed, but it can change from one form to another. And be careful here. If you say neither here you have to say nor. Don't say neither here and then you change it to or. You miss a point again. Right? Or if you don't want to use the words neither nor, you can say energy cannot be created or destroyed, but can change from one form to another. That's a different version where you are trying to avoid using the words neither and nor. All right, so you can say energy cannot. So you use the word not here. Neither means not, and this not should be followed by an or. All right, so we are saying energy cannot be created or destroyed, but it can change from one form to another. What this means in essence is that the total energy of the universe, all right, the total energy of the universe is constant. No part of the total energy of the universe can be destroyed, but it will simply change, right? In other words, the energy which a body may lose should be gained by another body. None of it is destroyed or disappears from the universe. All right, from the universe. The universe here is referring to the entire expanse in which we live, the planets, the heavenly bodies, the terrestrial and celestial bodies together makes a universe. So the total energy of that universe, of the expanse in which we live, the expanse in which there are bodies such as planets, the trees, the earth, and all that is there, the stars, the total energy in that universe has never been destroyed. All right, but it simply changes from one form to another. So if you don't want to say this statement here, simply say the total energy of the universe is constant. Constant means unchanged, is not destroyed. Okay, none of it is removed from the universe. Is actually a constant. Is constant. It simply changes. It simply changes from one form of energy to another form of energy. Please be able to state this in a very correct manner in an exam. By being so careful about the use of neither nor. Don't replace these words with either or. No, the moment you say that, it's like you are saying energy can be destroyed or something can happen to it that will reduce its magnitude in the universe. So a question that says state the law of conservation of energy. You have to say this one, all right? Energy can either be created nor destroyed, but it changes from one form to another. Or simply put, the total energy of the universe is constant. Great. So I'm sure you got it. All right, the law of conservation of energy. So using an example of an oscillating pendulum, we can demonstrate the law of conservation of mechanical energy. All right, so we can show the principle or the law of conservation of mechanical energy by a simple oscillating pendulum. All right, so the procedure is simple and straightforward. All you have to do is set up the apparatus as shown in the diagram below. All right, so this setup here is known as a pendulum. All right, this ball here is called a pendulum bob, which is attached to a string. All right, and is supported somewhere there. The support here can be something simply like a clamp and the stand. All right, or retort stand, sometimes we call it. All right, okay, so you attach a string to which a mass is attached, so that this mass can be displaced this way, so that it will be free to swing it from one point to another. All right, so if you give this bob here a small displacement, suppose you give it a small displacement, all right, you just swing it free using a hand. So you push this to the left, all right, at a small angle theta here and leave it so that it can oscillate. All right, so it will be free to oscillate from point A to point B to point C. All right, so that you have an oscillation like that, all right. So as it is oscillating, it is also changing its mechanical energy. All right, for example, when you push this to point A, you are displacing it through a height, this one, okay, with respect to this position here, which is the horizontal, right? Okay, so when you displace the bulb at an angle theta, right, to point A, you have given it a height. Remember that when a body has been displaced to a height with respect to its original position, it gains an energy form which is called the gravitational potential energy, or simply potential energy. So it acquires or gains potential energy there, so that upon being released, it is going to be changing. The energy it has is going to be transformed from potential energy here, because of this height here, it is at a potential, it has potential energy there. So when it goes back to point B, that potential energy is transferred or transformed to energy of movement, which we call kinetic energy. So it will change from a potential energy at the end. So here it has a maximum potential energy, which is because of the height it is at. Remember, potential energy is mass times acceleration due to gravity times the height h at which it is. All right, so it is oscillating. It was led from A to B. All right, in so doing, the potential energy, the energy of height there, will change to a different form of energy, which is kinetic. So all the potential energy which it has at A changes to kinetic energy here at B, so that at the point B, the bulb will have its maximum kinetic energy. Then it will proceed from B to point C, again at a height h. In other words, the height at B with respect to C increases. So there is an increase here of height. So that height will make the bulb acquire another form of energy, which is the gravitational potential energy. So what is happening now is that from potential energy at A, the energy changes to kinetic energy at B, which changes to potential energy again at point C. So as it swings from C back to B, it also gains the energy which it has there becomes kinetic energy, and so on. So the process continues on and on, until the bulb is damped, or it stops oscillating. All right. So they will ask you to describe the energy changes which take place in a pendulum. All right. So when you swing this by hand to that angle, we say you give it a displacement. All right. The ball or the bulb will gain potential energy, gravitational potential energy, so that when it oscillates on its own, it will be changing. The potential energy changes to kinetic energy at B, changes to potential energy at C. All right, and the energy changes back. The potential energy changes back to kinetic energy again, and to potential energy. So in that case, no energy is wasted. The energy which the body possesses at one point becomes a different energy that it possesses at another point, so that the mechanical energy is simply changing and none of it is being lost. But sometimes, because of frictional force here between the string and where it is attached, all right, this energy can be transferred to heat energy. That's why the body eventually is going to come back to rest, okay, on its own, because of the frictional force between the string here and the support it has, the contact, all right. Eventually the body is going to oscillate. They will ask you in an exam to state, why does an oscillating pendulum eventually come to a rest? Why does it come to a rest? Why does it eventually stop oscillating? There are two causes. There is friction between the string and the support where it is attached, and also in this space here there is air. There are air molecules. So as the body is moving this way, it is receiving an air resistance opposing it in the different direction. All right. So that friction, rather air resistance, and the frictional force there will cause the body to eventually stop moving. All right. At that point, it does not mean that the energy it had is destroyed. No, it has simply changed into other forms. All right, so that's what this setup is all about. So the procedure continues. All right, so you displace the bulb through a small angle, which we call the theta, as shown in the figure. Then observe what happens to the bulb. So we said that the bulb is going to oscillate. It oscillates from point A, where it has gravitational potential energy, to point B, where it has all of its energy becoming kinetic. Then from B to C, it will proceed, it will also undergo an energy change from kinetic to potential energy. So it can be observed that the pendulum oscillates from point A to C, then back to A through B. All right, as we illustrated there on the diagram, the body will oscillate. In this case, the pendulum, the bulb, is going to oscillate from point A to point C, then back to A through B. So the maximum heights, which are the points A and C, at those points the bulb stops for a very short time. We say in physics momentarily. It will stop momentarily, all right, and appears to move very fast from either A to B at maximum speed at point B. All right. They will ask you, where does the body, at what point, A, B, or C, does it have a maximum speed? All right. So it has maximum speed as it is passing through point B. So we are saying at maximum heights, all right, which are the points A and C, the bulb stops for a very short time. It stops momentarily. All right, momentarily means for a very short time, and then appears to move faster as it passes through point B. All right, with reference to the diagram there, you can actually rewind and see that what we are talking about. So we can explain or describe the energy changes from A to C as follows. At point A, in the diagram there, the body has maximum potential energy, while at point B it has maximum kinetic energy. All right, maximum kinetic energy, and at point C it has maximum potential energy again. So the bulb has its maxima at A and at C. All right, maximum potential energy at A and at C. All right, because that's where it gains its maximum height. Remember that potential energy has to do with height. All right, so at point A, the height at point A is the same as the height at which the ball has at point C, and the height at this point B is at its minimum. So it has all the potential energy at A now changes to kinetic energy at B, and all the kinetic energy at B changes to potential energy at C, and so on. So the process goes on and on until the bulb is damped. To be damped means to stop oscillating. It stops oscillating due to air resistance, the air molecules that it is passing through in the course of its oscillation. All right. So between points A and B, and between points B and C, the bulb possesses both potential energy and kinetic energy. All right. So as it is oscillating, midway between A and B, the body has both forms of energy, namely potential energy and kinetic energy. So it also applies between points B and C. Somewhere in the middle, the body will have its both potential energy and kinetic energy. So therefore, in this case, at any particular point, the total mechanical advantage, call it E, is equal to potential energy plus kinetic energy. So this sum is always constant, which agrees with the law of energy conservation. As energy changes from potential to kinetic energy, all right, none of the total energy is wasted. Energy is the energy of the universe is constant, right? Or energy cannot be destroyed. No energy is destroyed or created. All right, it simply changes from one form to another. In this case, it changes from potential energy at A to kinetic energy at point B, then kinetic energy, potential energy at C. All right, so potential energy at A becomes kinetic energy at B, which changes to potential energy at C. But midway between points A and B, the body has both forms of energy, which when you add up, it will give you the total energy which the body has as a matter of energy content. All right, so that's the explanation of what is going on the oscillating pendulum, showing that energy cannot be destroyed or created. It simply changes from one form to another. We can also demonstrate the change in energy using what we call a loaded spring. A loaded spring, all right? A loaded spring. All right, so a loaded spring is one on which a mass is attached. All right, so when you attach a mass to a spring, such a spring is called loaded spring. Okay, loaded spring. All right, so you set up the loaded spring as shown here. All right, as shown in the diagram. We have a diagram there that we can demonstrate. Then you displace, you pull it, you displace the spring vertically and observe what happens. All right, so you displace. To displace means to give it what do you call this, an amplitude. All right, you give it an amplitude, all right, so that it can swing, all right, it can swing or oscillate, all right. So you displace the spring vertically, meaning that from top to bottom, okay, along the vertical path. So you displace it, you just hold it, pull it down, all right, you give it that kind of amplitude, all right. In other words, you increase its length, okay. So the spring will be observed that the spring oscillates from point A to B to C, then back to B, and then back to A, all right. So we are saying it will oscillate from A to B to C to B, and then back to A, all right. So as it is doing that, its energy is changing. Its energy is changing. The energy of the mass changes, okay, from potential energy to kinetic energy to potential energy again, and back to where it started. So the energy changes in the block can be shown, all right, can be shown here. So we have a spring, this is a spring, all right, this is a spring. So you displace it. Displace means pull it down. Just pull this one down, give it a force, all right, pull it down, all right, so that it will be able to oscillate. So this mass will oscillate. To move, you pull it down initially, pull it down, all right, okay, you pull it down to point A, all right. When you release it, all right, when you release it so that it oscillates on its own, it will go to B, then to C, then back to B, and to A again. So it will be going up and down, up and down, up and down, up and down. So when it goes down here, okay, when you pull it, you give it a displacement, all right, okay, you are giving it a form of energy which is going to be changing from point A to point B. All right, so at point A, it will have a maximum kinetic energy, then it will have a maximum potential energy, sorry, and also that potential energy will go back to kinetic, so that here it's going to be, or to have its maximum kinetic energy, and then again potential energy there. So the energy will be changing from potential energy to kinetic energy, and then to potential energy again. So the energy changes that take place in the spring, all right, you give it a displacement, it is going to be oscillating up and down, all right. So the energy will be changing from potential energy at A to kinetic energy at B, and then to potential energy at C, and again to kinetic energy again at B, so that the energy changes from point to point. All right. Let us look at an example involving energy changes, or the law of energy conservation. So this question here is asking us, what is the velocity of an object dropped from a cliff? A cliff is a height, all right, a cliff of height of 20 meters just before it strikes the ground, all right. So here all we are given is the height at which it is, the height at which an object is. So we are asked, what is the velocity of an object dropped from a cliff? A cliff is a tower, something like a tower, something which has a height, all right, okay. So it has a height of 20 meters. This is a height, and from bottom to at the top, where the maximum height is 20 meters, all right. So the ball, or rather the object, is dropped from this 20 meters height so that it strikes the ground. Okay, so we are being asked what is the velocity of an object dropped from that height of 20 meters just before it strikes the ground. So we need to apply energy changes, the law of energy conservation. So when the body is at a height of 20 meters, it has potential energy. Why? Because of the height at which it is. Alright? So at the height of 20 meters, the body has potential energy. So when it is dropped from that height to the ground, all its potential energy now becomes kinetic energy. In other words, energy lost, not destroyed. Okay, by the way, lost and destroyed are different concepts. Alright, here this lost is simply referring to a change. Yeah, so potential energy changed or lost is equal to the potential energy which the object gains at the bottom of the cliff. Alright, so we are saying potential energy, the energy it has at a height of 20 meters will change to kinetic energy. Alright, so as it is about to strike the ground, all its potential energy has now changed to kinetic energy. So remember, somewhere in the topic we said that potential energy is found by multiplying the mass of the body, all right, by the acceleration due to gravity and the its height. All right, mgh, potential energy. Don't forget that. It's mgh. All right, so its mass multiplied by the acceleration due to gravity, which we are given here, and this is going to be equal to its kinetic energy. Remember that kinetic energy is found by simply taking half of the mass multiplied by the square of its velocity. Very important. Right, so the energy is going to be transformed. Potential energy becomes kinetic energy. Potential energy at the height of 20 meters, when the ball or the object is dropped to the ground, its energy is going to change. All its energy is going to become kinetic when it falls to the ground. Alright, so it has the maximum potential energy at the height h or 20 meters and the maximum kinetic energy when the ball reaches or is just about to reach the ground. Alright, so all its potential energy changes to kinetic. So if you look at this equation here, you find that mass is appearing on both sides of the equation. We have mass there, we have mass here, so this we can be cancelled. Alright, so you can cancel this and this m here as well as this one because it's appearing on both sides. So that when you make v the subject of the formula, alright, you take the square roots of both sides, alright, you are going to have this expression here, equation, alright. So we are saying v, the velocity, is equal to the square root of 2gh. Velocity of the body is equal to the square root of twice acceleration due to gravity multiplied by h. How does this come about? You multiply both sides here by 2, alright, and make v the subject. It will give you this one here. Okay, you can try this one mathematically. Make v the subject. It will give you v equals to root of 2gh. So upon substituting, so we know G is 10, we are given here is 10, all right, and the H is 20 there, so you multiply 2 by 10 by 20, okay, you should be able to get 400. So you take the square root of 400, the square root of 400 on your calculator, or without it, you find that the speed is 20 meters per second. Please master these steps. These steps are based primarily on the conversion of potential energy which the body has at a height of 20 meters to kinetic energy which the body gains. So we are saying energy lost by a body, not destroyed. This does not mean destroyed, just it simply means changed. So energy lost by the body should be equal to energy gained by the same. All right, then you make V the subject. From here it will give you V equals to root of 2GH. So upon substitution, you find that V is equal to 20 meters per second. Also, don't forget the units of velocity is meter per second. All right. So when you are solving this in an exam, you may be entitled to a number of marks. For example, by just saying this equation here, you already have a mark. And then you have another mark for transforming the equation so that it looks like this, all right, where you bring in mgh and half mv squared, all right, and then making v the subject of the formula will also give you a mark. When you substitute correctly, you get another mark, and so on until you get the value of v, the value of. Let's look at yet another example. This one involves a girl of mass 25 kgs is rolled down from point A to point B as shown in the diagram. All right, so we have this girl here. All right, she's rolling on this slide, all right, so she's rolling from point A. This is point A, all right, point A, which is at a height of 3 meters. This from the ground. This is 3 meters. All right, take note of that. All right, so she's sliding through a slide down to point B, all right, which is at a height of 0.5 from the ground. This one is not touching the ground per se. It is still suspended in the this part here, point B, is still somewhere above the ground, but at a height less than the original height. So in this case, it is at 0.5 meters. Please take note of these heights. So if the pull of gravity is 10 newtons per kilogram, calculate the potential energy of the girl at A. What is her potential energy at A here? How much potential energy does she have at this point? All right, how much potential energy does she have? Okay, and also using the same information, what will be calculate the kinetic energy midway between points A and B. Midway, it means somewhere here. All right, so if she's here in the course of moving, it means she's at a height half of the original height. So half of this is you can actually see it is half of 3 is 1.5. All right, so halfway here, what would be her kinetic energy? All right, so as she's sliding, there is energy change from potential energy. There she has potential energy, so the potential energy is now changing to kinetic energy as she is sliding. So in other words, the potential energy that she has there has half of it will be kinetic energy, midway, all right? And then we can calculate also the speed attained by the girl just before reaching point B. Just before reaching point B, what is her speed, all right? So all these can be answered, all these questions can be answered basing on the law of energy conversion, all right? So from point A to going down to point B, all right, the energy, potential energy there, potential energy will change to kinetic energy. Excuse me. All right. Okay, so that's the situation we have. So the girl, in the first place, has a mass of 25 kilograms. And we are given these values. The height there is 3 meters. Whereas point B is at 0.5 meters. So we are saying gravitational potential energy at point A is equal to mgh. Remember, potential energy is calculated as work done against gravity, which is mgh. Alright? Potential energy is mgh. Mass times gravity times height. So substituting the mass, we are told that the mass is 25 kgs and the height is 20 meters. So you multiply the 3. You actually get something like mgh. This is supposed to be 10, all right? This is 10, rather 3. Okay, so yeah, okay. So we have mass times acceleration, all right? This is supposed to be 10. The value of g is 10, not 20. All right, this is supposed to be 10. Please change this to 10, so that when you multiply these 25 by 10, it's going to be 250. Then multiplied by the height, the 3 meters, it's going to be 750. Please change this one to 10. The value of g is 10. Is 10, not 20 here, so please take note. So the mass is 25 kgs, acceleration due to gravity is 10. It's supposed to be 10 there, multiplied by 3, which is going to give us 750. That's great, that's great. So midway between A and B, it means now we are looking at half of the distance. So the energy lost from A to midway through B is going to be, potential energy will change to kinetic energy, all right? So that midway P, potential energy between points A and B is going to be half, all right? Because now the distance has reduced to half. So you take half of the original energy. So half of the original energy, the potential energy there, now becomes kinetic energy. So the energy is going to be half of the energy that it had before sliding. The girl had before sliding from point A going down. All right. Okay. So to find the kinetic energy she has, just take half of the energy that she had originally. Midway means halfway through, half of the distance. Half of the distance. So substituting, you take half of that, it will give you this expression here. So you take half of 750 joules, it will give you something like 375 joules. That's great. Therefore, the kinetic energy midway through the distance is going to be 375 joules. The speed attained can also be calculated based on the law of energy conservation. Remember that the potential energy lost is equal to the kinetic energy gained by the body. So you bring in the expressions for potential energy, which is mgh. So mgh is equal to half mass times the square of the velocity. All right. Once again, you see here m is common, is appearing on both sides, so you can deal with it by simply cancelling, by cancelling out. So in this case, velocity is going to be, the speed is going to be root of 2gh. Don't forget, this is the formula in energy energy conversion. So we are saying that when the potential energy changes to kinetic energy, this equation is very important. We're saying the potential energy lost by the body becomes the kinetic energy gained by the same body. So bringing in expressions of each form of energy, here we have mass times gravity times height, all right? Okay, which is the expression for potential energy. So mgh is the expression for potential energy, which is changed to kinetic energy, which is given by half of mass times the velocity of is square of the velocity. So if you make v the subject of the formula here, you get v equals to root of 2gh. All right. So all now you have to do is to substitute the given values. We know that g is 10, all right, and the height is 0.5. The 0.5 there, the 0.5 which is given. All right, the 0.5 is given in the diagram there. This is a different height. It's no longer the 3 which we we had earlier on. So the result is going to be 3 point in your calculator, just to be sure. Another example is going to be of help. We are looking at a ball which is being thrown upwards, vertically upwards, meaning from bottom to top, with a velocity of 15 meters per second. So calculate the maximum height reached. Alright, so here we are looking at a different type of question where the energy is changing from kinetic to potential energy. Alright. So according to the law of conservation of energy, the kinetic energy lost is equal to the potential energy gained. Alright. Okay. So when you throw something up, the energy change, remember that at its lowest point, the body has a maximum kinetic energy. So when you throw it up so that its height increases, its potential energy increases. All right. So potential kinetic energy changes to potential energy. So all you have to do is bring in the expressions for each form of energy. We are saying here the kinetic energy is half mass times the square of its speed. This is equal to mgh. So what is the maximum height? We need to find this height here. The fact that m appears on both sides of the equation, you can cancel this, you can cancel, so that eventually what you have is v squared equals to 2gh. So making h the subject of the formula, all right, just substitute so the values that are given there. So v is given as 15 here, and g is 10, obviously. So we can solve for h. You can solve for h. So in this case, you have, if you raise it 15 to the power 2, that's 15 times 15. It will give you 225. 225. So this is equal to 20h. All right. So solving for h will give us 11.25. So the maximum height is going to be 11.25 meters. All this we are able to do because of the law of conservation of energy. Energy is neither destroyed nor created. It simply changes from one form to another. So raising a body will change its kinetic energy to potential energy, so that you are able to bring in this equation and you solve for what they ask you for. So therefore the maximum height reached by the body is going to be 11.25. 11.25. Okay, I hope so far so good. The law of conservation of energy. Energy is neither created nor destroyed, or the other way around. It's neither destroyed nor created, but it changes from one form to another. So we are able to solve these problems based on that fact. All right. So lastly, we come to a very important part of the topic, which is energy work theory. Energy work theory. So some would say work energy theory. All right, what does it say? Okay. The energy work theory states that, so you should be able to state this, just like you are able to state the law of energy conservation. All right. So the energy work theory states that the net work done by the net force, okay, on a rigid body, on a solid, okay, on a solid body, rigid. Okay, this body is one which cannot be compressed or its particles shattered or scattered. It's a solid, all right? It's a solid body, rigid, all right? So we are saying net work done by the net force on a rigid body is equal to the change in kinetic energy of that body. That's what the energy work theory states. In other words, what it means is that when the work is done on a body, its kinetic energy changes. That's all it means. Its kinetic energy changes. So the theory means that when work is done on a body, its kinetic energy changes from initial kinetic energy to final kinetic energy. All right. So when work is done on any body, think of any body, solid body, all right, which is rigid, not one that is compressible or one that is that can easily be scattered or dismantled and all that. No, we are looking at a completely solid body. All right. So for a solid body, the work done on it, the net work done on it, all right, by a force. Remember that work is done when a force is applied. All right. So the work done by the net force, or the resultant force, as we call it sometimes, on a rigid body is equal to the change in kinetic energy of that body. That's what the energy work theory states. All right, so we are saying when you do work on a body, all you are doing is to change its kinetic energy. So the change is usually from initial or the starting kinetic energy, the certain value of kinetic energy, to final kinetic energy. So this change can be represented by an equation. An equation: work done is equal to change in kinetic energy. When you do work on any body, that is going to be equal to the change in its kinetic energy. But what is work done? Remember, right from the onset of the topic, work done is force times distance. Alright, force times distance is equal to the change in kinetic energy. Alright, so let's obtain an equation which gives us this change in energy. Okay, so we are saying work done, W, is equal to the change in kinetic energy. So this delta here is a change, yeah? Alright, change. Alright, so change in kinetic energy. Work done is equal to change in kinetic energy. So this change is usually final kinetic energy minus initial kinetic energy. So what is making the difference here is the values of the speed. Remember that final speed is represented by V, while initial is represented by U. Okay, so the final speed or velocity V, initial velocity U, so that the final kinetic energy is given by half of mass times the square of its velocity minus half of the mass multiplied by the square of its velocity. Now, if you look at the definition of work, we said work is force times distance. Remember that distance is represented by the letter C in motion. So for work done here is going to be force times distance. So the force times distance, which is work, is equal to the change in kinetic energy of the body. So this is the expression for the energy work theory. It says that the work done by the net force, right, on a body is simply equal to its change in kinetic energy. Kinetic energy. So we can obtain this kinetic energy by deriving it. All right, we can derive this expression mathematically. We can show how this one is arrived at. Okay, which is I also expect you to show in an exam, to derive it. Okay, to derive. So the net work done by the resultant force, we know that work is equal to force times distance. This is the starting point. All right, so work is equal to force times distance. That's how we start to derive this expression. All right, so applying one of the laws of physics which you are yet to meet in Form 4, this is called Newton's second law of motion. All right, the force on a body is equal to its acceleration multiplied by its mass. The force applied on a body is equal to its acceleration multiplied by its mass. This is a very important equation, yeah? Okay, you're going to meet this in Form 4 when you're looking at laws of motion as stated by Sir Isaac Newton. Alright, so again from Form 3 work, we looked at the equations of linear motion. One of the equations is this one here. V squared is equal to U squared plus twice the acceleration multiplied by the distance moved. Make sure you know this one. There are 3 equations, of, if not 4, which are very, very important in linear motion. So we are simply borrowing from those equations so that we can derive our energy work theory. What does energy work theory say? It says that the work done, the net work done by the net force is equal to the change in kinetic energy. That's great. All right, so with that on your mind, you can make A here the subject of the formula. So making A the subject of the formula here, it will give us, okay, you move this V squared to the other side so that you have 2AS. Then you divide both sides by 2S. Then A is going to be this expression here. So you can substitute, now you can substitute this expression into the where there is an A, you can put it here. All right, so that force applied is going to be equal to this, which is A multiplied by mass. All right, so work done by the resultant force is expressed in the following manner. Work is equal to force times distance. All right, but we said force is AM or MA. All right, so MA is force times distance S. All right, but we just said that A is this one here, V squared minus U squared. All right, that's what we said. All right, so multiply the mass by A. This is A, which is this one we obtained from this equation here. Then you multiply by distance, this distance. So we have this equation here. So if you look at this, you find the S is common here. There's HS there. There's also S here. So this can easily cancel out. You can cancel this out. All right. So the S will cancel this one. This is not seconds. It's the distance. I should have made it bigger because the way it is, it looks like a small S. But it's not a small S, it's just distance. All right. So removing or expanding this part here shall give us, shall lead, if you try to simplify this one further, the S is disappearing because it's cancelling here, it's multiplying. All right. So expanding this shall produce this expression here, which represents the change in kinetic energy of the body. So therefore the theory is obtained. So the theory is obtained. The equation, the equation above there is this one, which we obtained by derivation. So work is equal to net force multiplied by distance, so it's equal to this change. All right, please go through this many times, understand the mathematics involved until you get this one, because it is part of your syllabus to derive the energy work theory. Unless you have questions on this, but if you have questions, don't hesitate to send your question to me through the number that you have on the first. Let's look at an example. We are told here that a constant force of 20 newtons is applied on a trolley of mass 0.5 kgs on a flat frictionless surface. All right, So if the trolley starts from rest, if it starts from rest or from 0 and moves a distance of 1.5 meters, find the velocity of the trolley. Alright, so the mass of the trolley is given to us as a 0.5. 0.5, all right. Zero 0.5 on a flat frictionless surface. If the trolley starts from rest and moves a distance of 1.5 meters, find the velocity of the trolley. Okay, so all we have to do is to use the energy work theory. Use the energy work theory. The energy work theory says the net work is equal to the change in kinetic energy. All right? So the net work done is force times distance. So this force here multiplied by the distance. Okay, and we are told that the mass is 0.5. Okay, so the body is moving from rest. From rest, it means that u is equal to 0, right? Is equal to 0, so all you have to do is substitute. Substituting each given value into this equation. Force is 20 newtons, distance moved is 1.5, and u is 0 because it is moving from rest. Starts from rest means 0 here, 0. All right, so substituting, we have this equation here where mass is 0.5. So all we have to do is solve the equation for v. Solve it for v. So you make v the subject. So in this case, you have 20 newtons multiplied by 1.5 meters, which is 30. You take 20 multiplied by 1.5 is 30 newtons, right? Okay. So multiply this again by half. You take half of 0.5, you get 0.25 v squared. All you have to do is solve for v. So v is now going to be the square root of this one here, all right? And you end up getting the square root of 120. Okay, so the velocity therefore is going to be 10.95. So please go through the calculations. It's just a theory based on this theory here. All right, that net work is equal to change in kinetic energy. So work done is force times distance. Change in kinetic energy is half mass times the square of the final velocity minus half of the mass multiplied by the square of the initial velocity. Then you substitute, you should get this one here. Let's look at another example. Here we have a frictionless, a frictional force between the wheels of a motorbike and the ground is 150 newtons. The air resistance acting on the motorbike, sorry, I repeated this one. This is supposed to be on the motorbike, and the cyclist is 90 newtons. A driving force of 960 newtons is applied on the motorcycle, on the motorbike, by an engine over a distance of 50 meters. If the total mass of the motorbike and the cyclist is 180 kgs, and it starts from rest. Alright, find the resultant force on the motorbike. Alright, and then Find the final velocity of the motorbike. And finally, the acceleration of the motorbike. Take your time. So there is, once again, there's frictional force. Frictional force is the force that opposes motion, as we saw earlier on, all right? But the air resistance acting on the motorbike, on the motorbike, is 90. Okay, so here we have two opposing forces. We have this 150 newtons and this air resistance. Both of them are opposing the force of 960 newtons. All right, so to find resultant, you just take the driving force. Here is the driving force is 960 newtons, and the opposing force is the sum of the two. This one here, 150 newtons, which is friction, and the 20 newtons, which is due to air resistance. So you just add this and subtract from 960. It will give you the resultant force. These are vectors. So you're finding you have two forces acting in the same direction, and these are opposing another force of 960 newtons. So it will give the resultant force. The resultant force. So to find the resultant force, all you have to do is subtract. The applied force is 960. So you subtract the applied force minus some resisting forces. The sum of, this is supposed to be the sum of, like adding SUM, not this one. Alright, so we are saying the resultant force is simply 960 minus the sum of the two resisting forces. This is frictional force, and this one is air resistance. Just add the two and subtract from the total applied force, which you get as is 720 newtons. Please check the mathematics involved here against mine, so that you can correct if it is not in order. The final velocity of the motorbike is given by the energy work theory, or the work energy theory. What does it say? The work energy theory, all right, states that the net work done on a rigid body is simply equal to the change in kinetic energy. So don't forget that, okay? So substituting, work done is force times distance. Change in kinetic energy is half of mass times the square of the final velocity minus half of the mass multiplied by the square of the initial velocity. All right? So substituting again, you know, this is starting from rest, so the initial velocity is 0. So we are solving for v. All right? We are solving for v. So multiply out, you get 3,600. 3,600 is equal to 90. This is 90. Half of 80 is 90. Check that this is in order again. All right. So solving for solving for v, you actually see that this is this should be for the check here. The mathematics involved. All right. So you take the square root of 400. It will give you 20 meters per second. Please check that this is in order. If you take the product of the product of 720 times 50. 720 times 50 is 3,600. All right. So here it's 92 into 180 is 90. So you divide both sides by 90 here. So divide by 90. it will give us 40. So this one is not it's not actually 400, it's actually 40. So you take the square root of 40, take the square root of 40. So take the square root of 40, square root of 40. What is square root of 40? You take square root of 40. Alright, to take square root of 40. Take square root of 40. You find what do you find? Okay, square root of 40. Actually 6. So this is 6, yeah? Please correct that, do that correction. This is 6. 6.3. So the velocity is going to be 6.3 because dividing here, it cannot give you 400. Alright, so that's what we have. That's what we have. Now to calculate acceleration, we can use this equation here. Force is equal to mass times acceleration. This is Newton's second law of motion. All right. So solving for A, this is very serious. Solving for A should actually give you here is supposed to be, we are making A the subject, all right? So this is supposed to be, A is going to be equal to F, yeah, F divided by, ensure M, all right. Yeah, so that's what we have. That's okay. All right, so our F is 720, which we found earlier on over here. All right, and our M is 180. All right, 180 kilograms. All right, so all we have to do is divide 720 by check calculator. This should give you what? You divide 720 by 180. It will give you 4 meters per second square. Okay, so that's what you do. All right, please check the anomalies on the calculations. The anomalies on the calculations. So this is supposed to be 0, and cross out this square root. Square root of this one should be 6.3. Square root of 40. Meters per second. So that's what we have. So this brings us to the end of the lesson today, and indeed the end of the topic, work and energy. It has been an exciting topic according to me, and I'm sure according to you too. I believe you enjoyed the lesson, the topic, the presentation, and you have learned something out of it. Remember that when you are back to school, immediately you are back to school, The second week, we are going to have a test. We're going to have a test. A test in which you write, you have these topics examined. Alright. So, before we go, you are going to do this work here for me. So, a force of mass this is supposed to be a body of mass. Change this one to body. This is body. Alright, so we are saying a body of mass for 8 kgs moves through a horizontal distance of 20 centimeters from rest. If the force acting on the body or stone is 10 newtons, calculate. So you calculate the work done by the applied force, the kinetic energy of the body gained, and the final velocity. So you would make use of the energy work theory to solve this particular problem. So this is kg. This is supposed to be a kg. So over here we have a kg. Alright. So this, once again, this marks the end of our topic. Okay? Otherwise, I wish you all the best as we meet again tomorrow in a topic called machines. That's going to be topic number 10. Machines. Right? So that will be the work we are starting tomorrow, and we continue the same to next week. We'll be looking at machines. Machines. Thank you very much. We stop here for today. For now, bye-bye.